I've failed in one thing, which is to state our theorem that it's corollary of our two. We have two results. One is a Morse function with no critical points, a cobordism Morse function with no critical points as a product. And second thing, a cobordism with a Morse function with one critical point corresponds to a product with a handle in it. Okay. Then the sort of the corollary of all of that is that any cobordism including a closed manifold. Remember, closed manifold is a special case of a cobordism from the empty set to the empty set. So closed manifolds. Decomposed into products and handles. This is, I'm not going to bother stating it more precisely, just product, then you add a handle, then another product, then you add a handle, and then a product, you add a handle, and you're done. Okay. And everything is compact, so it's a finite number of those. Sometimes people will say that these are elementary cobordisms, and this, that's the story. One thing I've used the standard topologist definition of cobordism, and I've been discussing with Bruce, who's got a category theoretic better category theoretic understanding of these things than I do, because if you've never seen this before, one can just say there's this category whose objects are manifolds and morphisms are cobordisms between manifolds. And why is this like a category? Well, you can glue two cobordisms together. So there's something called the cobordism category. This another way to say this, and is sort of any morphism in this category can be decomposed into elementary morphisms. One thing that if you want everything to work right, you have to be kind of careful about saying what I said. Objects are manifolds. Objects are, well, for each dimension there's a cobordism category. Objects are n-dimensional manifolds. Morphisms are n+1 dimensional cobordisms. You can stick them on top one to the other. I won't say anything more about this, but one way to get this really right is to say that, so objects equal, and then Bruce, you can correct me if I say something wrong, and then a morphism from M0 and 1 is, there's two things yet. So it's a diffeomorphism class of the following things. So it's a cobordism X from M0 to M. Well, it's just a cobordism X from something to something. Okay, let's say from X0 to X1. And diffeomorphisms from M0, Mi to Xi. So this is a little bit, M0, and then when I say diffeomorphism classes of these, two different cobordisms from different things. You have diffeomorphism between them, and commuting with these diffeomorphisms. But the point is that you actually need to set up these if you just say, for example, 0, 1 cross n, its n's are not n. They're 0 cross n and 1 cross n. Those are different than n. Right? So you have to be really careful. You have to say I have diffeomorphisms. And in particular, if you're going to glue things together, if you just say, well, their n's are diffeomorphic, so let's glue them, well, you have to say, how do you glue them? And what's the way to glue them? So that's just something you may see in some other context, attempts to. I think there are a few other ways to try and make that careful, but I won't really use that language anymore. You can mention it.
Can I ask a
Yeah.
question? So do you have to worry about like ordering, like direction? Like I mean, a morphism, I guess, has like an input.
Right. You sort of you. So
These like all
in cobordism, when you say X is a cobordism, you have declared
I see. So there's
some
sort of
subset of its boundary components to be input and some subset of its boundary components to be its output. And if you shuffle them around, you could take the same manifold and declare different ones to be input and output, and then it's a different cobordism. Okay. And then I haven't talked about orientations at all, but you can also, if you have oriented manifolds, well, we'll do this eventually. But if you have oriented manifolds, then there's orientation conventions on top and bottom. Okay. Well then, for those who want to know anything more about it, if you start putting corners on things, you have cobordisms between cobordisms, right? Like you can have a cobordism, and then you can take for example, that cobordism across the interval would be a cobordism between cobordisms. That becomes a manifold of corners, and that somehow appropriately done is what's called a two category. And there's a whole story about that. You can ask Bruce more about it. Okay, so what I want to do next is I want to continue with examples. But I just wanted to emphasize this is now like a structure theorem for them. Right? I'm emphasizing the cobordism point of view, but if you just cared about closed manifolds, this means any closed manifold can be built by starting with a zero handle. It's got to have a minimum, right? And then attaching handles, maybe more zero handles, and then eventually capping off with an n handle. You're done. Closed compact. So back to examples. Let's see if I can mention 3. Let's see where. Yeah. So there's a special situation. Well, let's see. How to draw pictures. The one other thing is to say is this decomposition then is what is sometimes called a handle decomposition. Okay. So that's the order here. Handle decomposition. And so I want to say, how do you draw a picture of a handle decomposition of between them? So how to draw a handle decomposition. Or in other words, another say is how do you describe a three-manifold with a diagram? So what you want to do is, so first you have the zero handle, and we just draw a picture of the boundary. So the one handle. So draw the picture of the boundary of the zero handle. Well, that's a two-sphere. I want to make things as easy as possible. So let's puncture it once and think of that as R2. So this equals, so the boundary of the zero handle is S2, which equals R2 union infinity. And now I'm going to get a little sloppy about some things that I'll try to be more precise about later. I'm going to start saying, generically we can assume and things like that. These are transversality arguments that we want to be careful about. Okay, so so we're going to assume that the attaching maps to the higher handles don't go to infinity. Well, infinity is just a point. You're attaching something, and well, actually that's not technically true. When we get to the final top dimensional handle, it's got to go over everywhere. So attaching maps, except for the handle. Let's also assume there's only one zero handle. Okay, now we'll talk later about why you can do that. I'm going to be talking a connected three-manifold. Okay, let's also assume only one zero handle. And so these are some assumptions that I want to be more careful about.
Did you say we're assuming it's closed?
Yeah, let's say it closed. Yeah, let's say closed. Closed, connected. Let's say a closed connected oriented. Okay? So this is, there really ought to be an abbreviation for closed connected oriented. That I've never seen one. Everyone always says, writes all those words down. They always write them as an afterthought too.
So what,
Oh, by the way,
what about compact? Because
that's implied by closed.
I can say.
Closed means compact. Okay. Yeah. So we're just going to draw pictures here in R2. Here's R2, right? So we just here's R2 boundary 0 handle, 0H, 0-H stands for 0 handle, and now we're going to start attaching one handles. And so a one handle is attached. Well, what's a three-dimensional one handle again? Three-dimensional one handle is equal to B1 cut B2. So that's this. And let's try to over my coding conventions. Red was the attaching region.
Yeah.
Red was attaching, and blue was so. So that means we need to embed, so attached with S0 cross B2, right? So if we have a single 0 handle, we attach a 1 handle, right? So we just have to draw two discs, right? And so we draw a disc, right? Let me do that. So we have to draw the attaching map, the image. First I'm going to draw the image of the attaching map. So this would be a particular 1 handle, for example. So what you're supposed to picture is behind the blackboard is a ball, and then I've got a handle coming on. And I mean, if I like to draw, actual three-dimensional pictures, I could do that, but I don't really need to. I can just say that I'm drawing the attaching map. So again, something being pushed under the rug here is that two things. One is if I know just knowing well, I guess this is fairly straightforward. Just knowing the attaching map determines the diffeomorphism type of what we produce. But actually just knowing the image of the attaching map determines it as well, provided we have this assumption that it's oriented. If it wasn't oriented, I might have to say that, one way to think about it is suppose I take an oriented basis here to the boundary, and then if I go over and across the handle, it should come backwards. And if it came back this way, it would actually be an unoriented manifold, right? But we're just going to assume it's oriented, so just drawing the images of the attaching maps determines this embedding up to isotope. So we embed this into the boundary of the 0 handle, okay? And then the image, and this is what I'm speaking of as well, is that just the image of it, just drawing those disks, determines the embedding to isotopy. And then knowing the embedding up to isotopy determines the diffeomorphism type of what we produce. So now I might want to do a bunch of them, right? And so say I want to attach two different one handles, right? Then I do something like this. And then now, of course, the problem is which disks match up with which disks. So you need some convention. You could call them, say this is just label them A, A. Actually, no, it's what it's, backwards, right? Because, A happens to be symmetric, right? But B, since I'm really thinking of this handle as going like this, being backwards. And that's actually sort of useful to do sometimes. So now I need, okay, what if, already I've done something a little fishy as well. I said what you do is you have the 0 handle, and then you attach a 1 handle, right, because you've got a critical point in index 1. And now you might have another critical point in index 1, and that critical point is attached above, right? So why am I drawing it, attaching that down here in the 0 handle? Well, what I'm really doing, and again, I'm going to try to be more careful about this later, but give you some of the basics, its attaching map comes down, and generically I can assume that its attaching map, if I followed it all the way down with the gradient flow lines, would miss this 1 handle. So I've got a single 1 handle, I've got another 1 handle attached here, but I can just keep going down and see how it's attached to the 0 handle. I'm going to draw a lower dimensional picture of that in a minute, but the point is this one, you know, it might, if I'm really unlucky, it might happen that this one handle just hits right on the top of that one handle. But then by isotopy perturbation, I can slide it off. Although there's also subtlety that I can slide it off this way or that way.
And that's a handle slide.
That's a handle slide. Move on handle decompositions and Morse functions we discussed. So the idea is that if it's not generic and something ungeneric happens, then there may be choices involved in how you make it generic, right? Okay, so now the two handles are attached along this three-dimensional two handle. Oh, in my notes, I decided to call, I think this is sort of standard, to call an n-dimensional k handle, use a superscript for the dimension and a subscript for the index. Okay, so this is a three-dimensional two handle. It's P2, P1, and again, my picture of it now is I think there's a big flat disk. The discs on the top and the bottom are the free region and the sides. It's this annulus or cylinder. That's the attaching region. So now I can draw an attaching map somewhere, so you know, things might happen. For example, it might do, it might go over here, right? Let's be careful about thinking. So I want to draw. Okay, so well, one thing that might happen is I might just have forget about that for a second. I might just have a two handle attached here all by itself. Okay. The boundary, after I've done that, would have a single S2 component inside here, and then on the outside I'd have still this genus 2 surface that I've got, right? This is an example. I might do that, or I might have a two handle that actually goes over the one handles in some non-trivial way. I mean, the simplest thing, which is what we saw last time, is that the two handle might just go right over one of the one handles. Now, what does this picture mean? So here's this two handle, here's the attaching map of the two handle. I don't see an annulus, right? But the implication is that when it gets here, then it goes right over the one handle and back. Okay? So there's some understanding as to what happens on this part of the picture that's not drawn, that it's a product and everything, when it comes in here, it follows the product and comes out on the other side. Okay. So then this would be the convertible roof picture, right, where it could fold back down, and this would be actually these two critical points would cancel. Another possibility is, you know, there are much more complicated possibilities as well. Like, for example, I could have something go over, well, this is not much more complicated. I have something go from here to here, and from here to here. So now what's happening? It goes up, over, right? And it comes here and goes over. So this is really like the two handles are here, and then the two different one handles are here, my fingers, and then the two handle is so that picture just looks like this. There's the two one handles. And if you think about it, this is now, in this picture here, still everything cancels, right? Because I've got the two handle and then another two handle there. So actually this would still be sort of convertible roof picture as well.
Could you,
Yeah, go
I
through
was
that.
writing right when you drew those two extra things. So the two handle still follows it.
Yeah, so where does that two handle go? Where does the, well, okay, let me say one more thing. I'm drawing these, let me redraw this picture a little more efficiently and then try to address your question, right? So first of all, in principle, I could just draw points instead of discs, I claim, for the one handles. However, I'm going to keep them as discs because I want to remember if a point goes in and over where it comes out. Okay? So let me redraw that picture just as this. I'll draw it as A, B, B. Okay? And now, so you think of this as another way to picture is that there's this two-dimensional world, and whenever this isn't really in there, whenever you arrive there, you go up and you come across the other side. So now let me draw two different two handles. One of them, I'm just going to draw that only. Okay. And the point is that in a two manifold, which is where we're drawing everything, there's only one possible way to thicken up an embedding of a circle, to an embedding of an annulus. Okay? So I don't need to draw the whole annulus. I just draw the core circle. This is the S1. This is attached along S1 cross B1, right? But I'm just drawing the image of S1 cross 0, which is what we call the core circle. So I draw that. This one just goes up and over. What if I draw? So that's a particular. Let's call that. Let's just label it as X. Little a. Okay, we use little letters for 2 handles, right? And now that's a particular 2 handle. I can tell that it's closed off because this point is exactly this one. What if I go here, here? Where does this 2 handle go? It's here, over, here, and back. So it's closing up there. And so I can actually draw a more 3-dimensional picture of that.
It matters that A is there. Right?
Okay. Well,
Because
even if A was not there, I could still. So let's call it.
Sure, but that'd be different.
It'd be different, right? So maybe I'll draw the picture. So the more. Here's this. Really, this is capital A, this is capital B, right? And then little a is going up and over and across. Little a expanding like that, right? Little b is going here, up, over, back, the back side, and over, and insert that. And so, right, that's a very good point. The result then you can see again is one of these convertible groups, and I might as well not have attached any of them. However, if I did not attach little a, then it would not be the case. The result actually, so in that case, what would it be the same as? It would be the same as just attaching a single one handle. So this one handle and 2 1 handles and 1 2 handle would be the same as a single 1 handle. And that's also sometimes convenient to sort of think about. You could split a 1 handle into 2 1 handles and 2 handles connected. Okay. And then in the picture I had, I also had something like this, which then, you could do something.
You assume that there's only one in handle?
Right, so if I wanted to close this off, I would need two handles at this point. Because the boundary of this picture now, if I don't have this in here, the boundary of it is S2 again. Okay, but if I put this 2 handle in here, I've now split the boundary into 2 parts. Because that would be like over here I had a little 2 handle just attached like that. And now I've got a 2-sphere component on the inside and a 2-sphere component on the outside. And so now I have disconnected top boundary. And so there are various ways you could remedy that. You could just say, okay, now I'm going to close this off to attach with 2 handles. Or if you don't like doing it, I could, after having attached this 2 handle, I can actually attach a 1 handle now that connects the inside here to the outside. C, capital C. And this is sort of, what that would mean is that I've got, here on the inside, I've got a 1 handle. Now this is not, it's no longer going to work embedding this picture in R3. So I'm going to somehow come, this is that one will somehow tunnel through here and come out there. And now what does that do? That has the effect of reconnecting this interior boundary component to the outside, right? And then finally I would get an S2 boundary component again, and I can cap off with a single 0 handle. A single 2 handle. So I could draw this picture and then say a 3 handle, I'm sorry. I could draw this whole picture and then write union the 3 handle, and that describes a 3 handle.
But you don't even really need the same thing.
You don't have to. If by convention you're talking about closed manifold, then you don't need to say it. Sometimes in some contexts you want to be kind of clear that you are capping off or you're not capping off. Incidentally, this is not S3. Because if I didn't have this, so what happens is that there's actually a non-trivial loop here. So I'll leave this for you. maybe I'll give this as an exercise. Oh, I was thinking that maybe this coming Friday we'll talk about the, not this one, but the preceding assignment. So we'll take the day on Friday to talk about the preceding exercises, or however much time it takes. But the exercise right now is, let's do, just show that this picture by itself. So this is a, so this is a particular two handle. Let's, I'll go, I'm going to ignore all this stuff up here. So just A, and then A. So that's a one. So A, one handle, middle A, two handle. This picture, here's S1 cross S2.
But, so you should actually.
I claim that, you know, union, there's a zero handle and a three handle, and a single one handle, and a two handle that just is attached along this circle. So the two handle does not go over the one handle. And I claim the resulting three manifold is diffeomorphic to S1 process.
So we can assume this theorem that like this Morse function gives.
I mean, this is now, in a sense, there's no Morse theory now here. This is a building block description of a three manifold.
Okay, so you need to actually come up with like some.
So here's a three manifold I'm telling you how to build. Take a zero handle, attach a one handle at these two points, attach a two handle here. Then notice that the boundary is now S2, close it off with a three handle. You know, it's an embedding, you know, just glue a three handle on by the, you know, once you realize it's diffeomorphic to S2, then you glue a three handle on. Show that the resulting three manifold you get is actually S1 cross S2. And so that's, here's something now that I have, in developing this story, storyline said, well, okay, we attach this two-handle little c in this particular picture, and then I said, well, now suddenly I've got this disconnected boundary, right? Let me reconnect it by attaching a one handle to connect the inside and the outside. So I put a one handle on after attaching a two handle. It's sort of obvious that I could have just put the one handle on first and the two handle second. However, if you look at this example, there's no way I could put this two handle on before this one handle. Okay? So there's another general observation, which is you can always attach lower index handles before higher index handles, and we'll try to say that more carefully using a transversality argument next week maybe, or soon, but I'll just use your intuition. So you can always attach lower index handles first. And this actually, what does first mean? Well, in terms of Morse function, what would that mean about critical points?
It's critical value as well.
Right, you can always arrange, you can, given any Morse function, you can always, well, let me state this there, and we'll try to prove this later. Given any Morse function at, well, let's see, you can always homotopy f, any Morse function f, homotopy f, and it's just connected with a one parameter family of functions, f to a new function, a new Morse function, with the same all the same critical points. Okay, but the critical values of the indices of critical values are ordered in the same way that the values are ordered. Okay, but with, I'm going to write this, f of index k less than f of index j if k is less than j. Okay. So anytime you have things of different index, the idea is going to be proof deferred. But the idea is going to be that if I look at, suppose I have a lower index critical point above a higher index critical point, right? This is low, this is high, and I want to move this down. I'm going to take we're going to call the descending manifold, which is just all the, I'm going to take a gradient vector field, gradient-like vector field. I'm going to look at all the flow lines coming from this critical point down, and I'm going to argue that by a transversality argument, or generically, this will miss this critical point. And if it misses that critical point, I'm then going to modify the function in the neighborhood of that, all those downward flowing lines, and completely support it inside that, so as to just move this point down, right? And but we'll do that argument more carefully. I just want to assume and think about the consequences. The other theorem that I want to do is sort of at the same time, and is going to be this theorem that we can assume there's only, if the manifold is connecting, closed, so if the theorem is, if X is closed and connected, then there exists a Morse function on X with exactly dimensional, exactly 1 index 0 and 1 index 1. So that's something, and the argument there is going to be, suppose you have lots and lots of index 0 critical points. You want to argue that you can somehow cancel them with index 1 critical points at some point. And that's something we'll have to do carefully. Don't forget, I've never even proved to you that any Morse functions exist at all on a general manifold, and that's also, I also owe you that. That's a very different flavor. That's sort of analytic. That's proof about space of functions and so on. And I'm deferring that. But so yeah. But I want to think now about the consequence of these two facts regarding three manifolds a little more carefully. One more thing that is maybe easier is that I can always assume critical points have distinct critical values. That's just a small derivation. It's a similar idea to that. You can always move things up and down a little bit. So now, the corollary to three manifolds is the following thing. Given closed manifold X with a Morse function F, just say as produced by these theorems. In other words, it has one index 0, one index 3 critical point, and and the values of critical points are, the lower index critical points are above higher index critical points, right? Then, so now I'm going to draw an abstract picture of the three manifold. Index 3, this is mapping to R, okay? And so here's my index 0 critical point, and my index 3 critical point. They go to somewhere, right? And now I have a whole bunch of index 1 critical points and a whole bunch of index 2 critical points. So these are going to be index 1. You can be thinking in the back of your mind, why did I give them the same number? Index 2. Okay. And they're going to map to distinct points. Right? So there's some one, two, and then there's some special value in between, which is a regular value. Take a regular value, let's call that. So let's just assume this goes to A to V, and then this is some regular value T. So it's regular, so it's not a critical value, and it's between the index 1 and the index 2 critical points, right? Now I want to think about what F inverse of T tells us about it. So remember, this is entirely a schematic picture. This whole thing is really three-dimensional. This inverse image of T is codimension 1, so that's a surface, right? So you might want to remember that it's a surface. G is there or something, right? So that's a surface. And now let's think about, I want to think about how that, so that clearly splits the three manifold into two parts. And those of you who've thought about three manifolds know where I'm going. I'm going towards Haggard splittings of three manifolds. So in this situation, first of all, F inverse of T is a surface in X, which splits X into two pieces into, let's say, A, which is F inverse of little a up to T, and B, which is F inverse of B. So if we understand what these two manifolds are, then we can say there's these two different three manifolds that are glued together along some diffeomorphism from the boundary one to the other. Now, the next observation is that I can take, here's an important thing I haven't done yet, I can take just F restricted to B, and I can replace it with its negative, okay? So on B, consider minus F from B. Okay, then it goes from B to minus B up to T. Okay? And it will have a, what happens to the index, well, I'll just say R. And then the indices, index 3 becomes index 0, index 2 becomes index 1, and so it looks just like A. In other words, it has an index 0 and index 1. Okay. Now, a quick thinking about, we know pretty well what happens when you take a zero handle, a three-dimensional zero handle, and you attach a bunch of one handles. The boundary you get is a surface of genus equal to the number of one handles, right? Okay. So we know that the other thing then to say is that F inverse of T equals the boundary of A and equals the boundary of B, right? And we know that the boundary of A is diffeomorphic to a surface. Let's suppose we have, whatever haven't I used? Let's suppose I have K one angles. K index 1 critical points. Okay. Then we know the boundary, the A is equal to the surface of genus K. And that's diffeomorphic to the boundary of B, right? Because it's equal to it. So therefore, boundary of B is also equal to the same thing. And therefore, there have got to be K index 2 critical points up here. Okay? Because surfaces of the same genus cannot be different genus cannot be diffeomorphic because of the Euler characteristic. Right? To be completely pedantic about it. Surfaces of different genus are not diffeomorphic due to the Euler characteristic. So, therefore, there B has K. Well, actually, K index 2, or thinking about minus F, writing out minus F, it has K index 1 critical points. But now the other thing is to say that, as usual, I forgot. Oriented. So once I'm assuming things are oriented, we discover if I want to take a zero handle and attach a bunch of one handles to it, I'm going to attach k of them. Well, all that matters is where their feet lie, right? And that's just up to isotopy. So I'm just embedding 2k disks into a sphere, and any different way of embedding 2k disks into a sphere, if the orientations are consistent, is the same as any other way, right? I can isotope them around. So therefore, in fact, A and B are both diffeomorphic to each other, right? And both diffeomorphic to a solid, what's called a solid genus K handlebody. And a solid genus K handlebody, I'll just draw a picture of it for you guys. That's the obvious thing that a genus K surface bounds. But you can draw it either. So genus K handlebody, A is if you want to do this, solid ball, and then K and this any different way of attaching these K handles, K different one handles will produce different one handles. Of course, when you're first thinking about this, getting used to topology, you might momentarily make the confusion, well, what if there's a knot tied in this one handle, or these handles are linked together or something? But that's just, a phenomenon of the embedding in R3, which is totally irrelevant, right? Just as abstract manifolds, these things are diffeomorphic, no matter how I attach these handles, so long as I don't put an orientation reversing flip in there. And so this can also just be drawn, the more standard way to draw it is like this. And you just need to indicate somehow in your picture that this is the solid object, not that it has K holes in it. This is a solid object, not a surface. So the upshot then is that every every closed oriented three manifold can be constructed by gluing two solid genus K handlebodies together with some diffeomorphism from the boundary of one to the boundary of the other via for some K. So conclusion, and this is I suppose due to Haggard, but maybe, well, actually no, probably not. What I'm describing are called Haggard splittings, and I forget who first proved this. The first proof of this was not using Morse theory. It was using triangulations, and so I shouldn't obviously Haggard splittings. For every closed X3, there exists a diffeomorphism, that's a phi, from the boundary of, let me get this thing, let me say this, sorry, there exists some integer k, and a diffeomorphism phi from the from sigmas of k to sigmas of k. So this is a genus K surface such that X is diffeomorphic to index K, genus K handlebody, in another genus K handlebody, and the union is using this diffeomorphism. So you take two genus K handlebodies, that's the little a, the capital A and the capital B, and then you have some diffeomorphism, you glue them together, and that produces your three manifold. And so this is called a Haggard splitting. Sometimes it's useful to think of this surface as embedded in the three manifold and it splits it into two pieces. Sometimes it's useful to think of the three manifold as built abstractly from these two handlebodies by some gluing. I guess the last thing is to say, well, how might I nail down this diffeomorphism? Right? No, I think I'll leave it at that. For those who, well, if you think about it, this gluing map is how the top part is glued to the bottom part. Right? And remember, in the pictures we just drew, we were drawing, what this genus K handle body would have just been indicated by, in the plane, I draw K pairs of discs, right? And now, what about the how do I indicate what happens with this phi? Well, we just saw all you have to do is draw the attaching match for the two handles, okay? And so those are a bunch of curves that are drawn. And so it's interesting, that doesn't nail down this attaching map phi, but it nails it down enough to understand what the closed three manifold. So that's a subtlety about three manifolds that I may get back to. But I want to, I think I won't. Well, I guess I will say that. So maybe I should do this. So the question is how to diagrammatically describe the splitting or describe this construction. So let me think about it. So let me draw let's just draw genus two-handed body. I'll call it A, and I'll draw another genus two-handed body. B. And the first thing to think about is where are the one handles in A? So I can think of A, for example, as built by taking here's the zero handle, and then here's a one handle, and here's a one handle. Okay, so I can just draw this picture like this and say, well, that's A. Now, how do I describe how this is glued down to here? Well, in here I have let me think of this as built up of I'm thinking of B with its upside down Morse function on it. So it's got an index 0 critical point, index 1 critical point. So here in the middle is the 0 handle, and then going around this way is the 1 handle. Right? So and now, remember, inside of 1 handle, I've got a B1 cross B2. If I flip that upside down and think of it as a 2 handle, then suddenly the attaching part is the B2, right? So if this is a 1 handle going like this, if I want to think of it as a 2 handle attached going down, then the attaching region is, well, we just draw the attaching circle, the core of that region, goes like this and like that. Okay, so this, now I'll say that I'm running out of time, so I'm just roughly. Huh?
Swap your colors again.
Yeah, it's all. Well, it's now funny because things are upside down and right side up, so don't worry about it, right? But that's going to be attached down here, right? And so there should be some embedding of this circle and this circle down here, and it could, could be almost anything. Well, there's some constraints. It could be one go like this, and the other one can go like this. For example, it turns out that's actually exactly the picture I had before of a 1 handle. Here's a 2 handle running over this 1 handle, and then another 2 handle that goes over both 1 handles. Right? That's the same picture again. One thing you might, if you wanted to draw everything on the single surface, you might also say, well, I've drawn this surface, let me remember how it is that this surface is the boundary of something solid on the inside, A. So I can think, sort of flipping it over again, here's a 1 handle, if I flipped it over again, what's its attaching circle? And it would be this and this. So that was a super quick introduction to Hagar diagrams, which you'll see, Hagar diagrams, I draw an abstract surface of some genus, and I draw genus 2, let's say, and I would draw 2 simple closed curves on it in red, and 2 simple closed curves on it in blue. And what they correspond to is the surface is the middle level of the 3 manifold, And from one side, I have two handles attaching down here. Those are the attaching circles. I flip it over, I think the other side, I got two handles attaching down there. Those are the red circles. And so this is the kind of diagram that's manipulated a lot in one current approach thinking about three manifolds, which is Hagar-Floor theory, which gets three manifold invariants out of diagrams like this. We are out of time. Next time, I'm going to try to get to 4 dimensions.